All right, guys, welcome our video lesson for section 4I. So we're doing this virtually. I'm at home right now, so we're still messing with the technology a little bit, but so to kind of walk you guys through up to this point. So up to section 4H, we've learned about derivatives and we've learned about what they do. So the derivative is the slope of the line tangent to a curve at a given point. And we just recently ditched the limit form of the derivative. I mean, we explored it a little bit, but now we're getting into the rules for derivatives. And on the screen here, you'll see the first four we've learned. I did flip the order of number 2 and 3. I'll explain that a little later when I hand you guys kind of a study guide that has all the rules on this. But our first four main rules are constant multiple, power, and sum and difference. And these rules kind of work in conjunction with each other to allow us to find the derivative without having to use the limit form. They're useful, but they're very basic. And so the types of functions that we are allowed to differentiate using these four rules is kind of limited. And the rule we're going to learn today is going to kind of expand the ability for us to tackle different types of harder functions. And just to be clear, when I introduce this fifth rule, it will work in conjunction with these first four. So it's not like we're going to use number 5 and ignore these first four. All these, when we eventually get to the 10, 11, 12 rules, they all work together. To do that, though, we need to do a little bit of review of something we covered first semester, which was composite functions. Now, if you don't recall composite functions, those are the types of functions where you have one function going into another one. The notation for that was f with the circle. That's way too thick. We'll fix that. The notation was f with that little open circle of x, and that simplified to f of g of x. So we talked about how g became the input into the function f. So I've got a couple functions here. F of x is equal to 1 over x, and g of x is equal to x squared plus 1. Now, I know this is a recording, but at this point in time, what I'd like for you guys to try, and I'm going to do this a little later in the video as well, is just pause the video, and I'd like to see if you guys can evaluate these four composite functions. So the first one is f of g of x. The second is g of f of x. And by the way, we did do these back in unit 2, so don't peek. Third one was g of x, so g goes into g. And then the fourth one is f of x. So if you just watch the video straight through without pausing, I'll pause for about 5 or 10 seconds to give you guys a chance to pause the video and try these on your own. If you don't want to, that's fine. Can't make you do that, but I think that'll be valuable for the chain rule we're doing. So why don't you go ahead and pause the video and try these four. All right, so you either watch this straight through or you actually pause and try these. So the first one, f of g of x. So when we rewrite that, that's f of g of x. And so the function g becomes the input into f. So you're taking this and you're plugging it in there. And so the answer to that one would be 1 over x squared plus 1. I think you guys are getting a little more proficient in this because when we first did derivatives and you guys had to do the limit as x approaches, or excuse me, h approaches 0 of f of x plus h, you kind of get a preview of plugging x plus h in as your input into your function. That's one of the reasons why first semester we do composite functions, because I think it fits in well with what we have to do for derivatives. All right, the second one is g of f of x. And so now f becomes the input into g, which means you're writing 1 over x squared plus 1, which simplifies to that. And that's all you had to do on the first two. On the third one, g of x, so g becomes an input into itself. And this is one, since we're not studying composite functions here, we're going to not simplify this as much as we normally would. But g is an input into itself. So x squared plus 1 is the input for x, and it becomes that. And again, I would expect you guys, if we were doing this, to expand that to get the x to the fourth, but we're fine with that. And then f of x. I'm going to go ahead and skip that one because it's useful, but it doesn't serve the purpose for this video. So the idea of these composite functions where one function, the whole function becomes an input into the other one, is what we're going to use for derivative rule number 5. So what I want to do is I want to look at these three examples of ones that we could potentially do with our first four rules. So again, if we only have access to constant, constant multiple, power, and sum and difference, we could tackle all three of these. For example, the first one here, the x squared minus 4x plus 7 all over x to the third. At this stage in the game, I told you guys you are not allowed to find the derivative of quotients or products. And so because of that, how it's written, you cannot find the derivative. But what you can do is you can simplify. So if I rewrite this, f of x becomes x squared. And then since it's over x to the third, you can actually write each term in the numerator divided by x to the third. And so if we simplify that a little bit, f of x is equal to x to the negative 1 minus 4x to the negative 2 plus 7x to the negative 3. And now we have a function written in a form where we can use power rule, sum and difference, pretty much all our rules in this one except constant, but we're using the other ones. And so the derivative of this guy would be, and if you want to pause the video right now to give yourself a chance to do that just for practice, but I'm hoping by the time you're watching this video, you're proficient in finding the derivative of ones from section 4H. So this particular derivative is negative 1 x to the negative 2 plus 8x to the negative 3 minus 21x to the negative 4. And then if we rewrite that, f prime of x is equal to negative 1 over x squared plus 8 over x to the third minus 21 over x to the fourth. So just get comfortable adjusting those negative exponents back down to the bottom. The problem we're going to run into on G is, I don't know about you guys, but I don't want to really have to expand x plus 4 to the third, because x plus 4 to the third is really x plus 4 quantity times x plus 4 quantity times x plus 4. I don't want to have to expand that using Pascal's triangle and binomial theorem. It's doable, and even something to the third power, this is very manageable, and you end up with an x to the third, so a cubic polynomial. But again, it's a little more work than I'm wanting to do. And then what happens when you get to h of x and it's to the 10th power? Obviously, there's no way we're going to do that. And so there has to be a better way to do this other than just taking 2x minus 7 to the 10th power, getting all 11 terms in the polynomial, and then trying to differentiate each term. And it ends up there is a better way, a much, much, much more efficient way. And that method is actually called the chain rule. So I hinted at this in class, and it is one of those that when I give you the derivative rules, the chain rule will always be in play. It doesn't feel like it's in play sometimes, but it will always be hovering there, hiding, sometimes in the background, sometimes right at the forefront, but it will always be there. And what the chain rule allows you to do is it allows you to find the derivative of these really, really complicated functions without having to simplify, kind of like we did on this previous slide. I'm going to show you that there's a super easy way to find the derivative of actually both of these. They're equally easy using the chain rule without having to expand it. And that is the beauty of the chain rule. And so what is the chain rule? Well, when I show you the rule here, it looks a little complicated, and you might have to pause the video if you are writing these down, because I would highly recommend you writing these in your notes. Chain rule works when you have a function inside of another function. So think of these as composite functions. So f of x is equal to some other function, g of h of x. So h is the input into g. So it's almost like you've got these nested functions, kind of like if we go back to here, let's clear all the stuff off here, number, or g of x here, the function that's on the inside is x plus 4, and the function that's on the outside is actually x to the third. So you can think of this as a composite function where x plus 4 is getting plugged into the function x to the third. And that's what makes this, even though it doesn't look like it, it makes it a composite function. This one doesn't really apply. And then here, 2x minus 7 is the input into the function x to the 10th. So it's just a little more complicated. So chain rule works when you have a function inside of another function. And the way you do it is you find the derivative of the outer function, which in this case is g. That's why you see g primed. And then the stuff that's on the inside actually doesn't change. So whatever the function is on the inside, you just leave it, you don't touch it. But then the chain rule kicks in when you then multiply by the derivative of the stuff that's on the inside. Now, when you first look at this, even if you listen to what I just said there 2 or 3 times, it's going to be very confusing until we get into some actual examples. So again, find the derivative of the outer function, leaving the inner part as is, but then multiplying by the derivative of the inside, and that's the chain rule. That's what allows us to do it. So first example, we have f of x is equal to the quantity 2x plus 1 squared. Now, normally what you would want to do is you'd want to take that and you'd want to expand that polynomial to get 4x squared plus 4x plus 1, which is very easy, and then find the derivative of that. Well, I'm not going to do that. I'm going to use the chain rule. So the way the chain rule works is look at the outer function, which in this case is really something to the second power. So that is the thing you're going to have to practice when you're doing these derivatives, is seeing, kind of visualizing what that outer function is by just ignoring the stuff that's on the inside. So the outer function in this is x squared. So using our power rule, the derivative of f, so f prime of x, is equal to, so do the power rule. You take the 2 and you multiply it out front. And then the exponent lowers by 1. And then this is key. This is probably the mistake that I see most often when people first start doing these. The stuff on the inside does not change. So when you first do this outer function, do not change the stuff on the inside. Leave it as is. But now the chain rule part of that kicks in, where you now multiply by the derivative of the inside. And so the derivative of 2x is 2, and the derivative of 1 is 0 because it's a constant, and you basically have your answer. Now, usually with chain rule, there'll be some type of simplification you'll need to do. For example, in this one, I have a 2 out back and a 2 out front now that I'm going to combine together. And so this derivative becomes 4 times the quantity 2x plus 1. And notice it's to the first power, so I'm just going to leave that off. And then in this particular instance, we can simplify that by distributing the 4, and you get a derivative of 8x plus 4. Which, by the way, is exactly what you would get if I go back over here. What was this when we expanded it initially? It was 4x squared plus 4x plus 1. And if you find the derivative of that, you've got the power rule here. 2 times 4 is 8. There's our 8. Lower it by a power of 1. And then the derivative of 4x is 4. So if you're looking at this problem and you're thinking, why would I ever use chain rule when it seems pretty easy to just expand it and then find the derivative, is they're not always going to be that easy to expand. For example, the second one, we now have g of x is equal to 4 minus 5x raised to the 7th power. I don't know about you guys, but there's no way I'm expanding that to the 7th power. That is just not something I'm going to do. But the chain rule allows us to tackle this without having to do that. So if we do g prime of x, do the outer function, which in this case, the outer function is x to the 7th power. So we use our power rule. We multiply the 7 out front. You lower the power by 1 to make it 6. You do not touch the inside. You leave it as 4 minus 5x. But then the chain rule kicks in where you now have to multiply by the derivative of the inside. So the derivative of 4 is 0 because it's a constant. And the derivative of negative 5x is negative 5. And if we simplify that a little bit, again, you've got a constant and a constant. Just bring this guy out since you're multiplying. And so the derivative of this would be negative 35 times the quantity 4 minus 5x to the 6th. And that's how it works. What I'm going to go ahead and do is pause this video. So this will be video. No, I guess we can keep going on this. You guys can always fast forward through it. Let's go to a third example. It gets a little bit harder. We now have the function h of x is equal to the square root of 1 minus 3x. Now, this may not look like the first 2 examples, but it is exactly like the first 2 examples, just with a slightly more complicated exponent. So think back to what you did in section 4H when you had a problem that was this, and you had to find the derivative. Your first plan of action was to take that square root of x and change it to x to the 1/2 power. That is exactly what we're going to do right here. So this problem, this function h of x, I'm going to rewrite as 1 minus 3x to the 1/2 power. And now I'm going to combine together what I learned in 4H and what I've learned with the chain rule, and I'm going to find the derivative. So h prime of x is equal to, and now first plan of action is you attack the outside function. So the outside function is really something to the 1/2 power. So using the power rule, we multiply the 1/2 out front. You then lower the exponent by 1, so it becomes to the negative 1/2. The inner part does not change. But then you have to multiply by the derivative of the inside, which in this case, the derivative of the inside is -3. And so if I simplify that a little bit, now this one, I told you guys last week that any derivatives that involve square roots are kind of a pain. And so this one, you'll notice the simplification, kind of like what we did up here with the green one. You have to simplify it, but the simplification is going to be a little more complicated. Not bad, just a little more. So for example, I've got a -3 and a positive 1/2 that are being multiplied together, but I also have this guy, this 1 minus 3x, raised to the negative 1/2 power. So if you recall, negative exponents flip to the bottom. And so if I was writing the final answer to this one, I'd write it as -3 over 2 times 1 minus 3x to the 1/2. And I believe somebody in 4th hour had asked the question, do I have to rewrite this as the square root? If you wanted to, you could do this and write it as -3 over 2 times the square root of 1 minus 3x. I'm not going to require you to do that. This right here would be perfectly fine, but if you want to take it to the next level, you can do that. I kind of recommend leaving it here just because later on we're going to be doing the second derivative, and you're going to end up having to change it back to what's right here anyways. So there's really no point. I think that will be good. I will save, I've got some extra examples here, but I will save those for a separate video. That should at least give you an idea of what's going on. And then tomorrow, which is Friday, we might be back, but I'm going to guess not. If we're not, I will create a second video that'll walk you through some extra examples because some of these examples get a little annoying. And then your homework for today is going to be section 4I, numbers 1 through 6. Please make sure you skip number 7. The file that I will send will have a number 7, but the 7 is just, it's not worth your time. All right, so if you guys have any questions, feel free to contact me on Remind. Otherwise, good luck, and I will probably see you guys on